Welcome everybody to today's webinar. My name is Dan Combest, and today I'll be talking about automating CFD analysis tasks with Python and Helix. Today's goals: first, I really want to introduce ENGYS and some of our CAE innovations. I'd like to, have you learn more about the main features of the Python macro language within Helix, and overall obtain a sense of how a Python macro is created and run with Helix. So for the sake of time, we'll answer all questions at the end of the webinar, and we can continue via email post-webinar. If you actually hit reply on the webinar invite, that'll go directly to me so you can ask a question. Just a little bit of information about ENGYS. We are global providers of CFD software products and services. We were founded in the UK in 2009, and we're just now celebrating 10 years of being in business. We've always had a focus on enabling open source software in industry, and we've had a strong focus on foam, OpenFOAM, and we've been developers in this library since 1999. So if you're familiar with OpenFOAM, you know that before it was OpenFOAM in about 2005, 2006, it was a proprietary code called foam. So we have people on staff who have had a lot of experience with that, including myself. We have 7 offices worldwide in the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. And we have an established distributor network around the world in Japan, South Korea, here in the US, France, and also in Spain. Just a little bit of information about our products. We have several different types of products. The first one is Helix, which is a general purpose open source CFD software suite. And another one is Elements, and this is a superset of Helix, but more applied to the automotive industry. So there's advanced open source CFD tools for applying best practices for vehicle aerodynamics and doing other types of vehicle analysis. Next, we have Helix add-ons, and within that, we have adjoint optimization, we have block-coupled solvers, we have solvers specific for marine hydrodynamics, and then we also have advanced multi-phase flow solvers. Finally, we have Helix OS, which is an open source GUI for standard OpenFOAM. The last one, Helix OS, you can download for free. If you go to engys.com and look at our products, you can find Helix OS, and it'll give you a link to download that software. So before I actually get into the webinar, I would like to kind of announce a few events that we're going to be at. So we've got a few upcoming conferences. One here in the US is the 15th OpenFOAM workshop, which is in June. And if you're interested in submitting an abstract, you have 2 days left to submit that abstract. And ENGYS is the official sponsor of OpenFOAM Workshop 15. Next, we have the Brazilian CFD Congress, which is happening later this year, and we're one of the sponsors of that event. You can find out more information at engys.com/events. If you're unable to actually go to an event and you want to attend a virtual event like this, like a webinar, we have 2 upcoming webinars. One that I think will be really exciting is about machine learning for accelerated aerothermal design. This one will be given by one of our founders at ENGYS, our CEO, and he's really knowledgeable, Eugene de Villiers. And then I'll be giving one later in March about cloud computing with Helix and using a service called Penguin Computing on Demand. Both of these the links are on LinkedIn and on social media. You can also find it at engys.com/events. And then finally, our blog. If you'd like to go to blog.engys.com, you can subscribe for updates. You can see R&D notes. You can see past webinars. There's also information about continuous adjoint and about Helix and Elements. So it's a growing place to see content about our products and services. All right, enough of that. Let's talk about today. What I'd like to start out with is just briefly talking about workflow automation, talk about why add Python support, then dive into the Python macro within Helix, do a demonstration, kind of leave you with a little bit of thoughts on where we can actually apply these macros, and then some take-home messages. So workflow automation, in engineering school, we learn a lot about the engineering process, plan, analyze, design, build, test, deploy. That's this whole process, how we think as engineers. This is actually one of my favorite diagrams. So this is from Anthony Jameson, and this was in the optimization methods in computational fluid dynamics recently, actually a few years ago. And this diagram conceptualizes, more fine-grained this approach of plan, analyze, design, build, test, deploy. So this is applied more towards the aerospace industry. And one thing that you would note is it's about conceptual design and then also delivering a final design. So we've got two entry points right here. And then within these loops right here, we've got a lot of iterations over preliminary designs. And we've got CAD, we've got mesh generation, we've got CFD analysis, we've got visualization, and we've got this loop, this iteration over this cycle right here. We also have further evaluation of these results in other application areas for noise, stability control, structural, things like that. And then also we have comparison with simulations and with current designs with wind tunnel testing. There's building of these models to put in wind tunnels. And then there's also this keeping track of data. What I'm getting at is all of these loops are things that are repetitive processes. And companies spend a lot of time to develop best practices to drive these loops very efficiently. And they leverage methods that are known to provide results needed for design feedback. What I mean by that is there is some research and development component in all of this, but in order to reduce costs, a lot of times we really want to use things that are known, workflows that are known and proven. So we create consistent methods among team members. So if we have 10 people on the team and there's possibly 10 or more different ways to model the same system, if we create best practices and methods and routines, then we can have consistency between engineers if they're working together to do simulations and analyze a certain design. So it enables repeatable processes in order to decrease costs. So one thing that's important to note is that experts can do things consistently with high precision and accuracy. That's a very loose definition of what an expert is: consistent, high precision, high accuracy. So repetitive tasks are definitely an opportunity to reduce costs, so we can reduce time and money. We can also consistently apply expert knowledge. By doing it over and over and over again, we ourselves can become experts. And then also there's this potential to, if we're doing something over and over, to learn from other engineers and learn from past experience to apply it to this future repetitive task. It also allows you to seek support from other team members. So for example, if you have a junior engineer and you have something that's repetitive and you have something that's tried and true and you're confident in it, you can also hand that off to a junior engineer or even outsource that, insource that. But it also gives us great potential to automate and streamline. And all of this, however, there's this necessity to balance the cost to build and perform the automation versus performing by hand. So if it's cheaper to just, in terms of time and money, to just go and perform this, then that's the best way to go. However, if the cost to build these automations is really low and then running these automations, then it's definitely worthwhile to look into building these automating workflows. All right, with that, first off, why do we need to add Python support, or why would we even want that? Python is easy to learn, and I guess that's relative. But with other computing languages, Python is fairly straightforward to learn. It works across operating systems. So rather than using Bash scripting, which is also a great language, that would only work on Linux. And we'd have to redevelop those scripts in another language like Windows Batch or something like that. But with Python, we're able to work across operating systems. So there's several tweaks though, but I mean, for the most part, Python that runs on Windows can run on Linux. If you're doing something with system paths and things like that, then you might need to do a little bit of cleanup. Python possesses a rich library of mature and then also evolving tools. So there's a lot of people around the world that are continually improving Python. So it's really ideal because it's an evolving language. And because of its nature of being a scripting language, it's perfect for automating tasks. And we're not the only ones to recognize this. There's lots of other software. So it's a common interface between other software. For example, we've got FreeCAD, we have OpenCascade. These are both open source CAD libraries or CAD tools. ParaView has Python macro capability. Blender, if you want to do some post-processing and rendering. Rhinoceros, a proprietary software for managing and editing surfaces, that has a Python interface. Onshape, if you want to interact on the web, Onshape has a capability to use a Python API. And then also mesh generation from Pointwise and GridPro, both of those have Python APIs. So there's a lot of potential here to couple geometry generation, post-processing, rendering, and then also meshing and simulation. So back to my original diagram with all of the different loops, there's plenty of tools to kind of select and put together with Python support. So let me talk a little bit about the Helix Python macro language, some of the key features. So it's a new Python macro language to Helix, and we use this to automate the execution of Helix from the command line. It allows users to automatically build macro scripts with journaling. So this is really important because simply having an API, that's fine, but then you would have to really know the API or at least have some documentation and go through and do a lot of trial and error. But having this process of setting up a case visually through a graphical user interface and then having it record what you're doing, this is ideal. This is perfect because it lowers the barriers to automation. So going back to what I originally said of, if it costs too much to make, it's not worth it. Okay, so this really does a great job at lowering the barriers to automation. Right now, it supports mesh creation, case setup, solving, and then also post-processing. And overall, the process is, we use this macro language to drive all of these in sequence, or in theory, we could just break things up and do each one of these individually. For example, if you just wanted to generate 20 different meshes, you can do that if you want to do a sensitivity study on base mesh spacing to see exactly what your cell count might be. Or you might want to do something with case setup and running the code or running the solver. You could automate that. Or if you have a lot of cases and you want to make sure that you get the same screenshot from the same angle with the same size streamlines with the exact same legend on the left-hand side, then you can automate this post-processing capability or this post-processing on all of these cases that already exist. So the steps within the process, the first one is to create the script so users can record a macro in the GUI using the Helix journaling system. And the macros are written in the Python language, so that means that you can manually edit these if you need to. The next step is running the macro itself. You can run this via the command line, so in DOS or in a Linux shell, and then you can monitor the output. It'll output logs, it outputs lots of messages to the screen. And then finally, you can open up the case that's already been run. You can modify that case in the GUI. You can keep going. Or if you want to continue within Python and extract information from those cases, we could also do that. So the Helix macro language, one of the important things is that it looks like Python. Okay, it is Python and it's very recognizable how the structure is. So the macro file can be edited and modified using any external text editor. And we simply execute this macro file by, so this is on Linux because it's a .sh file. So this is the executable for, or the command to launch the GUI itself. And we pass it a flag that says Python execute. And then we give it the full path to the Python script itself. So that's all we have to do. There's other additional options that we could pass. For example, if we were running on a headless node on a cluster, or if you're familiar with the run modes and the run mode manager, you can pass it a specific run mode to run in parallel on HPC. So there's other flags that we can pass to this, but for now, this is really the only additional thing that you need to do to launch a macro. So let me start and do a demonstration and just walk you through the case. What we're going to do is set up the simple motorbike case. Well, not simple, this motorbike test case. This is a standard case within OpenFOAM. I've made a few modifications. There's some duplicate STLs, and then there's a really poorly resolved porous media in there. So I removed that just to make things a little easier on ourselves. And the goal today is I want to set up the meshing, I'll set up the simulation parameters, and then we'll go from there. So let me exit out of this. Let's go. So when you start Helix, I'm on Windows. So when you start Helix, you're met with this client server connection wizard. I can connect with other computing resources. So in theory, I could add my cluster back in the United Kingdom or our HPC resources in the US, and I can submit jobs directly from my Windows laptop here in St. Louis. These two right here are for my workstation back in my office. I'm in another building right now, but if we're only going to work locally, I can select localhost. Now you'll see right here, I've already got one running. I've got another one running in the background, which already has the results from the case. So we could either connect to that or I could start a new server. So we have these tools to manage these client server connections in order for us to kind of choose our resources that we want to use for a particular scenario. All right, so let's let it start up. So in this case, I could open up an existing case. I could choose something from this list. I could start a new case. So one of the important things of journaling is kind of the critical points is how to start, where's the starting point for journaling? So what I could do is I could load a case and start journaling, but then I'd have to create a new case. I could create a new case and then start journaling, but then again, I'd have to create another new case. So at this point, let me just close this and you'll see right here, this is ungrayed. I'm able to start journaling. So let's start here. And the important thing is that once you click this button and it starts recording your actions, it's going to do everything in terms of creating a case, moving a case, saving as a case. So we need to start journaling before we do anything like that in order to capture all of those actions. So let's start journaling. And then let me place this on my desktop. Let's double click there. And let's call this my macro.py. Let me see if there's another one on there. Whoop, there's one already there. Let's do my macro-v1. And let me hit save. And let's go all the way back out to my desktop. And let's find that before we go any further. All right, so right now, right off the bat, it's already inserted some of the requirements for the header, some of the different packages that we need to import into Python. So it's already inserted that. So one note I want to make is that I am working in 3.2.1, which is about to be released in the next 2 weeks. So right now, this is the testing version. This is the beta version. So I'm kind of giving you a preview of some of the different changes. All right, so we're journaling right now. Let me go to File. Let me create a new case. Let's call this motorbike dash. I think I've made a few of these. All right, so I'm not going to run this today, but if I wanted to, I can run on as many cores as I want. I'll go ahead and set it up for 16 to pretend that I'm going to run it on my workstation. Let me hit OK. And what that does is it sets up the structure of the case. It sets up several different text files. The workflow for Helix is we start in these different tabs. So we start at Mesh, then we go to Setup, then we go to Solver, then we go to View. Within each one of these tabs, we start at the top and we work our way down. So let's start with meshing. Let me choose the algorithm. We can either use the default layer addition algorithm or the dualized layer addition algorithm. I'll use the dualized because it guarantees 100% layer coverage. For the base mesh, we can choose several different types of base meshes. I'm going to have the software create a wind tunnel for me. And what we do with that is we give it the X, Y, and Z coordinates of the wind tunnel, and then it will create the background mesh. And then from there, we'll cut our surfaces into the background mesh. All right. One important thing is that we want to make sure that these cell sizes are identical between all these different directions. So let's do 40, 16, and 16. So the background mesh is going to be cells that are cubic with 0.5 meter in size. And so let's make the inlet. Let's make the outlet. Let's make the ground. And I'd like to have 3 layers on the ground. This will be the sky if we want to do like an open road type scenario. And then the min Z and max Z, this is going to be the front and the back. So let's call this one back. So if you're familiar with OpenFOAM, this is actually creating a block mesh dict for us. And it's going to use block mesh, the structured mesher within OpenFOAM and within Helix to generate a background mesh for us. All right, great. So there's my background mesh. Next, let me import my geometries. All right, so I've got 1, 2, 3, 4, 5, 6 different geometries or different STL files. I'm going to import this and have it convert to Helix binary format. The reason why is because if I do that, I'll be able to load the geometries much faster. It saves the case much faster. I don't need to worry about, I know that these units are already in meters. So some CAD software, the default length scale is in millimeters. So let's do 5, turn off parallel projection. All right, so here we are. We've got 5 different surfaces, but now you'll notice that there's a lot of different child surfaces. Before I go any further, let me make a searchable surface. We'll call this VR4. And this is going to be a refinement box. So let's do -1, -0.7, 0, 8, 0.7, and 2.5. And so here, I'm going to apply a volume refinement. So inside of each one of these cells, we're going to do, say, a level 4. And if you'll notice, I'm doing a level 4, and I also called it a VR4. I just do that out of best practice to make sure that I'm able to look at that surface and know that it's a VR4. So I can change it to VR5 and change this to 5. So it's just kind of a bookkeeping tool that I use. All right. So let's go back and let's look at the body of the vehicle. Now I've already broken this up outside of the GUI. Actually, I broke all the and grouped all of the different surfaces inside of Helix and then saved it in a previous case. That took a little while, so I didn't want to repeat all of that for this demonstration. So here, this is all the external body components of the motorcycle itself. So let me do a level 6 and a level 6. So this will be 8 millimeters on all of these different surfaces. If I want to, I can do something called proximity refinement, which means that if it's near another surface, it will increase the refinement up by 1 level. So that'll become a 7, that'll become a 7. One important thing, and let me see if I can hide this background mesh and then also hide this box right here. The way that the mesher works is it will do a walk over the surface, and if it sees a difference between the angle of the normals then it will refine. So you can see right here that if this purple and this green section, there's really, the normals are going to be very similar with each other between here and here. There's a potential that it won't resolve these boundaries of this STL because it's not changing its refinement. So what I like to do is let's highlight everything and then let's do something called snap surface boundaries. So what that will do is that will ensure that we resolve that delineation between these two patches. All right, let's talk about wheels. Oops, actually, one more thing. Let's go ahead and add layers while we're at it. So here, let's add 3 layers. We added 3 layers to the wind tunnel. Let's add 3 layers on the body of this vehicle. Let's look at the motorbike itself. These are all kind of the components inside of the motorcycle, something that isn't necessarily going to see or form a boundary layer with the external air that's flowing over it. For that, I'm not going to put layers on it. I'm still going to use layers or refinement 6.6. Let's do a proximity of 1. And then for the rider, let's do something very similar to what we did for the body. 6.6 and layers of 3. All right, great. Let's talk about the wheels. So these are all the different rotating components. I've grouped them all together. So there's disc brakes, things like that. Let's do level 6.6 and let's do a proximity. I'm not going to do any layers on this. And then let's do the same for the rear wheel. 6.6 proximity of 1. Now, I could have gone through and selected everything because everything is 6.6. I could have done that and applied that everywhere by holding down the shift key, and I can also use control key. Once we've got all our refinements, so our surface refinements and our volume refinements, then I need to select a material point. This material point will tell the mesher what side of these bounded STLs where all the physics and the simulation are going to happen. So for example, if I chose the material point inside of this tire right here, then it will mesh inside of this tire, which is what we don't want to do. We want it to be outside. So I can either grab it and move it. If I know the point, I can just punch it in there, or I can hit this point and it'll choose the center of all of the bounding surfaces. All right, so that'll work here. Now at this point, I could mesh and we could wait about 15 minutes on 12 cores. This machine only has 2 cores. And then we can have a mesh and we can continue. However, there's another capability called virtualization. And what this does is it assumes that all of our surfaces that we've got here will become either boundary conditions or cell zones. One important thing before I go on is here's a radiator. How do we set a cell zone for this? Let's go here to zones. I almost forgot about this. Set this to internal, set this to cell zone. All right. So this will become a porous media. We can apply a porous media model, Darcy-Forsheimer model, to approximate the pressure losses and momentum source term from the radiator itself. All right, once I'm ready to go, let's hit virtualize. And what this does is, it assumes all the surfaces will become boundary conditions later, but it also allows us to go further in the process and set up all of our boundary conditions. So we're in the setup tab. We start at the top and we select our solution state. So we're going to do segregated, steady, incompressible, so there's no thermal. Let's do air. For the turbulence modeling, we're going to do a RANS K omega SST. If this was transient, then we would have access to the LES DES. So most of these different boundary conditions are just going to be walls. So we can set this if we want. We can edit multiple. By default, everything's a no-slip wall. We can apply a wall pressure boundary condition if we want. Here's our wheels right here. And let's go ahead and set the inlet condition for the wind tunnel. So inlet, and let's set this to 40 meters per second. I'm not going to change the turbulence. And then for the front, let's also look at front and back. So I held down Shift key for that. Let's set those to symmetry. And then for the ground, let me set that to a moving wall. And let's do fixed tangential velocity. So it's going in the positive X direction. And let me set that to the identical inlet velocity that I've got. So this is a rolling road type simulation. All right, so there's ground. So ground is a rolling road, and then let's go and let's set our outlet condition. So we'll set outlet to outlet, and then let's set sky. We can either set that as an opening or we can set that as a symmetry plane. I'll just be easy and set it to a symmetry plane for now. Okay, so the rest of the boundary conditions, the ones that we really need to set are the actual wheels themselves. So if it's rolling road, then we need to apply a rotating wheel velocity. So it's a wall, but it's a moving wall, and it is a rotating wheel. So in order to do that, we need to set the center of rotation for the wheels. So we've got 0.013, 0, and 0.2987. The axis of rotation is in the negative Y direction. We'll use the right-hand rule. The contact radius is 0.305, and then the hub speed should be the same as the ground speed and also be the same as the inlet. So we'll set it to 40. Let's do something very similar for the rear wheels. So let's check this box in order to edit multiple patches. It's a moving wall, it's a rotating wheel. Now we have a different center of origin, center of rotation, 0 and 0.2987. We have the same direction for the axis of rotation. Now, if we were in a vehicle and there was tow or camber, or we had the motorcycle slanting, maybe it's cornering, something like that, then this axis of rotation would be pointing in a different direction, 0.305, and then also 40 meters per second. Next, let's set up the porous media model. And here I want to use a Darcy-Forchheimer. And at this point, we can apply our different experimental results for our viscous loss coefficient, our inertial loss coefficient. And then also if the radiator itself wasn't aligned with the Cartesian coordinate system, then we would need to change the E1 and E2 vectors. E1 is the principal flow direction of the fluid going through the radiator. And then E2 is an orthogonal vector to E1. And so it uses this to correct the orientation of the radiator with respect to where these viscous and inertial loss coefficients were actually captured experimentally. So if the radiator was just sitting on a flat table and you captured the experimental data for viscous and inertial loss coefficients, then we want to make sure that we adjust the orientation vectors of E1 and E2, which are local. We can do other coordinate systems. You can do cylindrical, but Cartesian works for this particular scenario. I'm not going to adjust these, but we could, in theory, change these different coefficients. All right. All the physics are set, the inlet, the outlet, the walls, the rotating wheels, everything like that's already set. Numerical schemes, I'll leave. Solver settings, I'm leaving. Runtime controls, I'm not going to run this, but if I wanted to, I could adjust the end time and how often it writes. Write data, we can export EnSite, we can export sets and surfaces. Surfaces would be something like VTK. So we can set up all of those. Field manipulation, this is great because it allows us to do in situ data processing. So we can do things like, let's generate Y plus, let's calculate Y plus, but I only want to calculate Y plus at output time, and I only want to write it at output time. Another one that I might want to do is near wall velocity. I like that one because it gives us the velocity of the cells just above the patch itself. And so on the walls, on the patch itself, it's 0 because it's no slip, but we like to look at this near wall velocity. Let's see, near wall velocity. Okay, great. So we can configure lots of different things. Vorticity, we can do individual operations on different fields within the simulation, and then there's already pre-configured things for heat transfer coefficients, Q criteria, Courant numbers, and cell Peckley numbers, wall shear stress, skin friction. So there's lots of different things to choose from. All right, let me leave that. Monitoring functions. Here, let me do a volume report. This will give me the min, the max, and the mean of whatever variables I pick. Let's just do UK, P, and omega. This will be over the entire domain. Also, let me do a surface report because I'd like to get a summary of the Y plus values. So let's do an area weighted average of Y plus. So Y plus is only calculated at output time. So I need to change the write control to output time. And then in terms of patches, I only really care about the Y plus on the patches of the motorcycle itself. So inlet, outlet, back, ground, front. I don't need any of those. All right, so I've got all of my different surfaces from the motorcycle and on the rider itself to get the Y plus values. All right, let me hit OK. That's already configured. I'm ready to go. Let's see initialization. Let's do potential flow initialization, and then let's do Prandtl for the turbulent parameters. All right, at this point, if I had a mesh, I would hit initialize, but since we're virtualizing, I can move on to the solver tab. If I'm ready to go and I want to launch the case right now, I can hit run all, and run all will mesh, initialize, and then run the solver all at once. So let me hit save. And then this whole webinar is about the Python macro. So let's go look at the Python macro itself. So everything that I've done in terms of starting with where I name the case, how many processors I'm creating this case for, the background mesh, I changed the names of that background mesh, I imported my surfaces and added these different volume refinements, or the one volume refinement added the box itself, and then added these different surface refinements. So it's recorded everything that I've done. So right here, this case, it's written 740 lines to this macro. So imagine if we didn't have journaling, this would easily take a few days to set up from scratch if you didn't have journaling. Just going through and flawlessly creating all of these different lines. So it's really powerful to go ahead and use this as a starting point and then go back and edit this manually afterwards. Now, to run this case, because I didn't run the case in the GUI, and like I said before, it records every action. So I would need to run a case.runAll function at the end of this in order to, when I launch this macro, in order to actually perform all of my calculations, meshing, initialization, and running. All right, great. So there's the macro. And when we're finished, we can post-process these different results. Here we're in the View tab. I'm not going to go through a demonstration of the View tab entirely, but you'll notice we can do slicing, clipping, streamlines, isosurfaces, and in 321, now we can do glyph vectors. If we want, we can group things together. So for example, I took all of those patches, all the dozens of patches for the different boundary conditions on the motorcycle itself, and I grouped them all together in one single entity, one single group called motorbike. And then I'm able to control all of the legends, what colors are going to be, what fields are being shown on each one of those patches. So that's called motorbike. And in this case, I've got streamlines, which were the velocity magnitude. If I wanted to, I could change the location. This is near wall velocity. So the surface of this motorbike, this is near wall velocity. Let's change the location to bottom. If I wanted to, I can change the resolution of this legend. I can change the color scheme. So there's lots of different things to choose from in order for customization. One other thing that I like is scenes, or our scenes. Scenes are something that we can use to consistently capture images at the same orientation. So I could create a new scene, but right here, I've actually got one already created where I change the background color to white. We can remove the display axis or remove the ENGYS logo if we want to. And let's just say that I've moved my mouse and I've accidentally rotated this thing around, but I want to get back to where I made this scene. I can go apply to view, and then I'll snap it directly back to where I had this nice image. So the great thing about that is that you'll be able to consistently get images at the same focal point, the same camera position, the same distance, and output these images. If I can do save to image, it'll output that each time. So when you make a presentation and you're presenting in front of a manager or in front of other stakeholders, it looks very nice when you go between slides. Okay, all of these controls that I talked about, we could, in theory, have just made a journal and control all of those things. So let me jump back here and let's talk about what we can actually do with macros. So macros would be great for performing a defined set of simulations over a design space. So for example, wind directions. If we had multiple different wind directions, if we're doing urban comfort, urban environment, we can automate this whole process of doing our different simulations for different wind directions. If we have a variety of geometric components that we need to switch out, like I showed you inside of the macro, it has a list of what these STLs are. We can automate that dropping process, that changing out of geometries. We could also drive a set of operating points that might be outside of the design space. So for example, if you've got a simulation and you recorded a macro, and then suddenly you need to run this what if analysis with hurricane force winds or some other wind direction, or maybe there's some marketing specific scenario. So there's lots of moments where some other group within your company might need information from your simulation, and this will save a lot of time if you've already created a macro for this. Like I mentioned before, it enables consistent data analysis for streamlines, images. It'll allow you to automate things, image dumping and data analysis for reports. So it's perfect for that. So known data points. The other one is optimization. So we could do shape optimization to do things like reduce drag, reduce power losses. We could also do optimization on the boundary conditions themselves to produce a desired chemical species. So what is the inflow of chemical A that comes in this inlet, and at what quantity in order to maximize an intermediate reaction, something like that. We could change the pressure values on outlets to balance mass flow rate. And then also we could do something called inverse design, where we change a parameter to achieve a target value. All of these different things, these first two, it's a form of inverse design. So one thing to remember is that running many cases is costly. So for example, if you're doing shape optimization and you figure that you're going to need to run 500 cases, and each one of those cases takes 10 hours and 500 processors, that's a lot of computing resources. There are other opportunities or other tools that can do these kinds of optimizations outside of this macro application area. For example, adjoint. So adjoint can do these kinds of things, and it uses a single mesh or a lot fewer meshes. So just to think about that. So there's also more complicated workflows. More complicated workflows would involve wrapping a macro in a Python function. So, well, right here, you can see that I've wrapped these different macros, or this macro that I've written, in a Python function, and I'm passing it some variable. And then within this variable, we can use it to, say, append a case name. So if I've got 10 different cases and they're going to have 10 different velocities, I can append different case names. So there's lots of different things to do with that. So wrapping all cases, whether you're driving points or doing an optimization, you're going to need to wrap the Python script in a function. It's probably It's one additional line and then an indentation. So optimization may require third-party optimization libs. So there's lots of different optimization genetic algorithm libraries within Python. Each one of them might have specific functional forms. So not just passing one variable, but you might need to pass an array of variables. And then you also, if you're doing a constrained optimization, you'll need to provide information about the constraints, and you'll also need to provide a return value of the objective. So not just driving the analysis, the meshing, the setup, the solving, there's this contraction of data, summarization of data, and returning that as a value if you're doing an optimization. So averaging drag over the last 100 iterations, something like that. All right, so let me leave you with a few take-home messages. Overall, a macro language based on Python is really an ideal automation and optimization tool. So it's very well known, it's very easy to learn. Journaling is key to lowering the barriers to automation. If we just had an API, that would be great, but it's not enough. You need something that has journaling. Individual components or the entire process could be automated, meshing, running, post-processing, all of that. In terms of looking ahead, running on HPC is possible and currently being tested. So running on multiple cores on your queuing system. So everything that we do right now with the client server mode is something that can be done within the Python macro with a little bit extra effort. And we're totally open to collaboration to connect with other Python-based tools. Welcome. So Rhino, meshing software, post-processing, rendering. So if you have experience in that, feel free to shoot me an email and we can talk about that. I'm definitely interested in sharing knowledge about how we can do this. And then finally, the maturity of the macro language requires use and feedback. So I'm totally open for feedback on the macro language itself. So if you're a current customer and you want to use this macro language, please go ahead and dive into it. If you need help to review how to get started, I can definitely help you with that. But feedback is very important for us to improve this tool. And that's all I've got today.